So, how this is going to work, so we have two operational mics. We have
Testing, sibilance. All right.
You like the sibilance.
This one.
That one's a lot louder.
Testing, sibilance.
So that she could go and give a talk about her. Like, she did a great job. Yeah, she was awesome. That was the only RE student we've ever interviewed before.
Yeah.
Before this program.
And to make sure they actually fluently spoke
Oh my,
Spanish.
I just, you know, I'm bilingual, so.
Not I didn't speak Spanish.
She was from Puerto Rico, so it was immediately it's like, okay.
We actually had Mercedes Lopez Morales interview her in Spanish.
Yeah.
Because we were like, the most important qualification for this job is that you speak fluent Spanish and that you can talk about science in Spanish.
Yeah, within 5 minutes, like Mercedes, like, yeah, she's good.
So neither, I mean, Chad speaks some Spanish, I know a little bit, but I think none of us would really consider ourselves fluent.
No.
So we had to ask her and see if they had find someone who speaks Spanish before Tatiana was with us. And we have our own native Spanish speakers.
Not with that. Like literally.
Have you heard from her?
She did a brief kind of like summer internship with Jenna, doing some satellites and some DE stuff on Hinode. So it's really good. So she's doing great.
And I would not give them You know, I think.
Are you excited?
Good morning, everybody. Good morning, John. Oh, hi, Kathy. How are we doing today? So, doing well? Fantastic. The students are great. So, not nervous at all. So, welcome to the 2023 Solar REU Symposium. So, I'm Chad Madsen. I am the PI of the program. I run this along with Kathy Reeves and Tatiana Niembro Hernández. So, 10 weeks ago, these students knew nothing about the sun. This is a topic that is taught mostly in grad school, and it's not something that's usually covered in an undergraduate coursework. So these students, over the course of just 10 weeks, had to learn everything they could about the sun, and then apply that knowledge into a novel research project. And every one of them had the passion, the skill, and the talent to work their way through it. And even though there were some trials and travails this year, so we all made it here. And we all look forward to seeing the results, the culmination of all the work that you've put in this summer. So in a few minutes, we're going to set up with our first speaker. And we'll get underway at around 9:45. So does that sound good? All right. So Katie, come up and we'll get you ready. Also, there are paper schedules if you want to follow along at home. They are in the back, right there next to the drinks. So, all right.
Let me share this one. Is that good?
Yeah. Let's turn it down. There we go. I guess so.
Oh.
It was a bit, yeah. We got to run the vacuum cycle again. It's going to be rough.
It's a little dark with the wall down.
It is a little dark. Let me see if I can get some lighting on.
Oh.
That's too much lighting.
All the lighting.
So.
The dark will just illuminate my figures.
Yeah.
Ooh, that's
There we go. We got a little bit of house lights. That's good. Thank you. All right. So, if I were to test this, can anybody hear me on Zoom? Somebody give me a thumbs up. Perfect. Okay. Yeah, you got a few minutes, but if you want to start maybe a tad bit early, you're welcome to. Maybe give about a minute or so.
Sure.
So, yeah. All right. Sounds good. Can you test your mic? Make sure it works.
Hello. Fantastic.
Perfect. All right, let's get your topic. Okay, and you were doing this on PowerPoint?
Yes.
Okay.
Hey Chad,
Yep.
on the Zoom controls under more,
Yep.
go hide controls.
Yep.
Hide floating point controls.
There we go. Okay, slideshow. Yep, it's on presenter view. Good.
Awesome.
All right, and yeah, you're welcome to take it away.
Okay, awesome. Well, good morning, everybody. For those of you who don't know me, my name is Katherine Joslyn, and for the past 10 weeks, I have been working with Dr. Nishu Karna and Dr. Tatiana Niembro on A Tale of an Intense Geomagnetic Storm in Solar Cycle 24. So we are trying to tell a story that follows a coronal mass ejection from before it erupts on the sun to when it interacts with the Earth's magnetic field. So first, it's really important to understand why we're doing this, and that has to do with what happens after the coronal mass ejection reaches the Earth. So coronal mass ejections can cause geomagnetic storms, and geomagnetic storms are what cause the aurora borealis, but they can also negatively impact the Earth. They can interfere with radio communication, GPS systems, satellites. They can corrode oil and gas pipelines, cause power blackouts, and can even pose a threat to the safety of astronauts. So it's really important to understand how and when coronal mass ejections evolve through space and interact with the Earth to then predict and understand and potentially lessen the impacts of the storms when they are interacting with the Earth. So, a quick overview. I've already mentioned a little bit about the story, but this plays an important role throughout the entire presentation. And more specifically, we'll be focusing on how the interaction between coronal holes and active regions results in intense geomagnetic storms. So I'll start by talking about the method, which will begin with the instruments used to observe the data, and then followed by the 3 models that I have been working with this summer. And then finally, we'll just briefly discuss where the project is going to go from here. So the first thing that I did was look at in situ data using the WIND spacecraft. And so what this is showing is different parameters of the solar wind at 1 AU across time. And so what we are looking for here is a signature of an intense geomagnetic storm. So we really want to look for the drastic changes in these parameters, and most specifically, we want to look at the bottom panel here, which is the SIM-H, which is the disturbance in space-time. And so that's what's going to tell us or indicate to us that we have an intense geomagnetic storm. So we want to look for a really low dip. And so initially, we identified the structure that is highlighted by the blue dashed line. And from that, we used a linear fit model to try to connect this in situ data with an eruption that we can see on the sun. And so when we actually went back and looked at the images on the sun, we realized that we have a much more complicated event than we thought, because there are multiple filament eruptions from around the same area within about a day. So so we thought that we wanted to initially trace back this one in blue, but we ended up choosing a specific filament that we wanted to model on the sun, and that ended up tracing back to the structure that is highlighted in red. So both will play a very important role in the future work, but in terms of the work in this presentation, we will be focusing on the structure in red. So as I mentioned, we went back and tried to connect the in situ data with both a filament eruption that can be seen in SDO-AIA, which is in this video, and was on the 13th of August in 2015, and then that can later be traced in the SOHO-LASCO coronagraph images a few hours later on August 14th. And so the reason that we wanted to choose this filament eruption specifically is that it is located really close to a coronal hole, which can be seen in that AIA image, that very dark spot. And this is important because our main hypothesis of this project is that coronal holes intensify the effects of geomagnetic storms. And so that's why we chose to model this one. And once we identified this filament, we were able to begin the modeling process. So the first model itself. The first model is a nonlinear force-free field model. So we believe that filaments, structurally speaking, are magnetic flux ropes. And so the best way to model them is by inserting a flux rope into the filament that we saw erupting in the previous slide. And so the goal of this model is to obtain a stable flux rope, which is when we adjust the poloidal and axial flux to the highest values before the flux rope erupts. And how we do this is we start with the two-dimensional plot, which is on the very left, and we take two cross-sections, which give us the one-dimensional plots seen in the middle, and these are the ones that tell us whether or not our model is stable. And so here we do indeed have a stable model, which we can see based on the shape and size of the dark spot on that one-dimensional plot. And then we also just have the 3D model so we can see what that flux rope looks like. So now that we have an idea of the magnetic configuration of the filament right before it erupts, we want to know what the magnetic configuration is after it erupts. So what we try to do is get an unstable model. And so very similarly, just again, adjusting the poloidal and axial flux until it erupts. And so for this one, we actually realized from the observations using SDO that the top of the filament doesn't completely erupt. So because of that, we added a barb to the filament so that we could give different axial flux values to the top and bottom of the filament so that we can get the bottom to erupt while the filament stays to more accurately match the observations. And so this movie here shows the cross-section below the barb and the evolution from 10,000 to 90,000 iterations, which is just through time, and shows that that structure is in fact erupting. And yeah, just a little further, this is again the unstable model at the 90,000th, just to give you an idea of now what that two-dimensional and three-dimensional plots look like. And then in red is where the barb was that we inserted. So now that we have an idea of the magnetic configuration of the filament, both before and right after the eruption, we want to understand how the coronal mass ejection behaves in interplanetary space and how it interacts with the solar wind. And so to do this, we will go back to 1AU and start with remodeling the in situ data, and that gives us the inputs for an analytical model, which will help us jump back to 10 solar radii, and then that will give us the inputs for a numerical model, which will, in very small steps, bring us back to 1AU. So the in situ data, this is very similar to the wind plot that I showed earlier, but again, just showing that in red is the structure that we are focusing on right now, and that's going to be our input for the next part of the model. So what we do, so once we finished the flux rope models, we kind of leave the magnetic field modeling behind because coronal mass ejections, when traveling through space, follow hydrodynamic models, which focus on velocity and density. And so because of this, from the in situ data on the plot on the previous slide, we take the velocity and density and use the second derivative, which helps us find the instantaneous changes in the parameters. So you can really clearly see the changes between very high solar wind and densities seen in white and then low in dark blue. And so from this, we take a very thin slice from the contour plots, and that is going to be the input that we will use to reconstruct this model back to 10 solar radii. So as I mentioned, this is now so in red is the same structure that we marked in the in situ data, but now back at 1AU. And so how we got this was by taking that thin slice or filter from the contour plots and putting them into Bernoulli's equation for the steady flow of an adiabatic gas. And so the two main or important features of this plot are the big gaps that you can see between the data points and then the plateaus, or the areas that are really dark because it looks like there are a lot of data points right next to each other. And so because we're using Bernoulli's equation and assuming a streamline, we have to follow the laws of conservation. And so the gaps are where the input data did not follow the gaps or followed the laws of conservation. And so we cannot use them in the reconstruction. And alternatively, the plateaus are really good data points because that's where the inputs did follow the laws of conservation, and that's what we want to focus on to get the input for the numerical model. So what we do is we want to focus on those plateaus, which are where we have conservation, and then we fill in the gaps in between, which is basically like filling this structure with a gas. And this is going to be our input for the numerical model. So now that we took one giant step with the analytical model from 1 AU back to 10 solar radii, this will allow us to see the entire evolution from 10 solar radii back to 1 AU. So this is the numerical model, and when we put the input from the previous slide into Euler's equations of conservation of mass, momentum, and energy, we get this, which allows us to see how the structure that we identified travels from 10 solar radii all the way to 1 AU. And so this just indicates that we were able to successfully trace this structure because we were able to match this with the observations seen on SDO and SOHO LASCO, and then the in situ wind data. And then, so the next step is to look at a more in-depth comparison of the in situ and then our simulation. And so here we have the velocity compared at 1 AU. So as we can see, they align pretty well, which shows that we did successfully trace the CME, which means that we can continue to move forward, and also we can reproduce this model in the future. And so the next step will be to compare the densities at 1 AU as well. So in terms of next step, we also have where the project is going from here. So because it is such a complicated event, we don't have any definite conclusions right now, but where we will be going moving forward is we can model all of the filament eruptions. So we can apply the flux rope model to all of the ones, which you can see all the filament eruptions in this video. And then we can even take the flux rope models a step further by calculating the helicity. And what this will do is tell us the Z component of the magnetic field strength in the in situ data, which plays a crucial role in understanding the intensity of the effects of geomagnetic storms. And then, similar to how we can reconstruct the magnetic field models, we can also construct the analytical and numerical models for all the eruptions to not only see how they behave and interact with the solar wind, but more importantly, how they behave with each other in interplanetary space, and then how that will affect the impact of the geomagnetic storm at 1 AU. Yes, so just acknowledgements. Big thank you to mentors and my fellow students. And questions.
Fantastic. That was fantastic. Thank you, Katie. I'm glad everybody could hear that. So right now we're going to take questions. If you're in the audience, raise your hand and I'll bring the mic to you. And then Tatiana will be monitoring the Zoom for any questions in the chat. Callie.
Hello. Can you explain like the gist of what a flux rope is?
A flux rope is basically just like the magnetic field configuration of a filament. So it's how we think the magnetic field behaves within a filament on the sun. And so it basically looks like we have a current sheet that runs a direction, and then you have the magnetic field lines running around, like going around it. And so that ends up looking like a twisted flux rope.
Jonathan.
Yeah, nice talk, Katie. When you're doing the analytic part, you have places, you explained there were the gaps where continuity didn't seem to apply. Do you want, can you explain, or have you any idea why that is? Why there are bits where the continuity doesn't apply?
I think that the fact that we have such a complicated event and that we have things interacting plays a big role, because we don't really know what's going on fully and we don't understand the full story when we're only modeling one event right now. But I also think just in terms of what's going on in the solar wind, there are a lot of outside factors that could play into that.
Okay, so it's just the analytic model is too simple to capture.
Yeah, because right now we're only focusing on like a few of the inputs of the equation, and we can continue to add even more variables and make it more accurate.
Any more questions? We have plenty of time for questions.
Anna has a question.
Anna.
So you mentioned about 10 solar radii. Is there a reason that you picked that value?
So that is an arbitrary value, but it's something that we can play with. So we wanted it to be within the region where we can see the LASCO images, so that we could align it with that data and make sure that we are following the correct event. But then we also needed it to be past the subalfanic region. And so we probably can work mostly within 10 to 20, but right now we're starting with 10, and that's something we can change moving forward and adjust.
Kathy.
So at the beginning, when you were talking about modeling the flux rope with the NLFF model, you talked about adding a barb so that you could control which parts of the filament erupt. Just for the uninitiated in the audience, could you say a little bit more about what you mean by a barb?
So I think that when you look at the filament on the sun, they a lot of times have these natural features that look kind of like arrows almost. And that often helps tell the direction of the flow. And so basically that we're inserting one of those. And yeah, it just kind of separates the different parts, and that's why we can apply different values to each.
All right.
You might have mentioned why this is, and I missed it, but you said at the beginning that coronal holes could maybe make the ejections more powerful, or am I correct in that conclusion, or and why is that true, if it's true?
Yes, so that is kind of our hypothesis, but it's because coronal holes are these regions of open magnetic field lines. So they're constantly pushing stuff towards the Earth. And so we think that if there's that stream coming from coronal holes, that when that interacts with closed magnetic field regions of active regions where the coronal mass ejections come from, that the interaction between the two of those can cause an even more intense storm.
We have time for one more quick question. Going once, going twice. Thank you, Katie. Up next, we have Lenice Bailey. We'll be talking about some lab work that they did. Let's see, let me end the show here. Yeah, probably that side because you'll be looking over that way. Let's see. Not that, oh yeah. Tricking me here. All right. It's all right. This is there we go. Yeah, there we go. That's more like it. All right. So, Lenice Bailey will be talking to us about some X-ray optics. All right. Take it away, Lenice.
Okay, can everyone still hear me? I'm not sure. Hello? Oh, is this on?
Hello? Hello? Oh, okay. Okay. So, hello, my name is Lenice Bailey, and my mentors are Peter Cheimets and Ed Hertz. And for my project, I'm working on advancements in X-ray telescope production using layered thin glass substrates and non-heating adhesive bonding. Now, to give a general overview of what I will be talking about today, I will first start off with a bit of history, then go into the goals I wanted to achieve for my project, which will then lead me to talking about the different networking I've done, talking to people both here at the CFA and at CDP, then talking about a bit of the lab work that I have done and the results I received during that time, to finally end on potential plans for the future. Now, I couldn't exactly just go into the lab and start bonding glass together. That is not very realistic. So I really wanted to focus on looking back and seeing what has been done, where did those procedures and methods fall short, and how I can improve upon them. And so with that, I wanted to focus on, there we go, these two specific methods. Now, for X-ray mirror manufacturing, there have been many methods implemented for these processes, but I wanted to focus on the uses of heavy mirrors and heat slumping. Heat slumping I will describe a little later. And now the reason why these fell short, these two main reasons, is the fact that it is quite expensive, the production value is really high, and then also it is not a very replicable process. And so with that, my idea is to bond thin pieces of glass together using an adhesive and using a process known as cold forming, which I will also describe a little later. So when I was first proposed this project, the main thing that I knew that I was going to be using was Corning willow glass, which is a very thin sheet of glass, which is about 0.1 millimeters thick. And as you can see from this video, it is quite flexible. And now this thinness of the glass is more ideal when trying to mold into a particular shape in comparison to thick glass, because thick glass will not flex in this manner. So with that, it led me into wanting to learn more about X-ray mirror history, talking about how they were made, what procedures were used, and what the results were having done those procedures. And to finally then talk about the different adhesives I need to use in order to bond my glass together. I wanted to focus on the viscosity, or how much it was spread. And with a bit of guidance, we decided to use epoxy 9313. So now, as I mentioned earlier, in X-ray mirror production, a common method that was used was heat slumping. And now, while this process has been successful for the production of some powerful X-ray telescopes, it is not very efficient. Firstly, it is not cost effective. In order to have a very smooth and polished piece of glass, you're going to need an equally, if not more so, smooth and polished mandrel. And if you want a lot of those glasses, you're going to need a lot of those mandrels, and the cost will just start to rack up. Secondly, with the heating, there's the possibility of contamination and losing your smooth surface. So by heating the glass onto the mandrel, which is the heat slumping process, where you have your thin glass, you have your surface, the glass is heated, molding to that surface, you remove it, and it should hold the shape. But with that process, anything that could potentially be wrong with the mandrel or the surface that you are molding your glass to could be imprinted on the glass. Any dust or any variations, that could go on the glass, and thus you would lose your smooth surface. And then finally, just in relation to the glass that I'm using, my glass is just way too thin and too weak in order to withstand the heating process. The heat would cause it to draw its temper and thus break. So then what are the benefits of cold forming, which is what I will be doing? Once again, it is more cost effective, as it does not require a perfectly smooth mandrel for production. Secondly, with the lack of heat, there's less possibility of contamination. And then finally, the process can be repeated. With a low production cost, we can have more glasses and more mandrels at a cheaper cost. So now, having gone through a bit of the history and the reasons why I'm doing it, what would be considered a successful X-ray mirror? And for that, it needs to meet the following criteria to be successful. Firstly, we don't want any air bubbles in my adhesive, as the air bubbles could cause any deformations when being bonded. Secondly, we don't want any dust particles. And thirdly, we don't want any surface variation between my reflective surface or my glass and the surface that I am bonding the glass to, which would be my mirror. And in order to check for these certain things, I will be using a microscope to check for air bubbles and dust particles, and an interferometer to check for the surface smoothness. And now, if I were to be very successful with my short-term goals, that would lead to the possibility of achieving these following long-term goals: great resolution, a larger collecting area, and all the while making it more cost-effective. Historically, for powerful X-ray telescopes, they had to sacrifice one of these goals in order to achieve the other, but hopefully if this process or my procedure is successful, we won't have to sacrifice any one of these. All of them can be achieved. So as I went through these 10 weeks, I realized that there are lots of things I do not know. Firstly, as far as glass cleaning, I can't exactly use soap and water. And as with the epoxy, I have never used epoxy a day in my life. And then also just trying to check for surface smoothness, I wouldn't know even where to start. And so this is where the importance of networking came in. Starting off with glass cleaning, I want to give a huge thank you to Suzanne Romain and Rick Bruni. For in their lab, I was able to come up with a method working alongside Rick to have my glass become spotless by using deionized water, methanol, acetone, and an ultrasonic bath. And in addition to this, my mentors and I felt it was important to have some of my glasses be coated to give me a more realistic view of what X-ray mirrors would look like. And by having my glass coated, I could see how my glass changes as a result of the coating, as well as see how it changed by it being bonded. And then as for the epoxy, thank you to Joe Zajac, because with this, we are able to use an outgassing chamber in order to remove any and all air bubbles from my epoxy. Essentially, in the outgassing chamber, all the oxygen is just removed from the epoxy, thus giving me a bubble-free adhesive. And then also he presented the idea to help with spread and also still removing any possible air bubbles by epoxy placement, placing epoxy on my bottom surface and my top surface when placing them together, hopefully giving me a better and more even spread. And then finally, a thank you to Jana Samra for showing me how to use the interferometer, because with the interferometer, which is this instrument right here, we're able to check for surface smoothness and compare the surfaces of my flat as well as my bonded surface to make sure that they are the same. So finally, very close to the end of my internship, I was able to get into the lab, and most of my data and time spent was using the interferometer and checking for fringes. To kind of give a brief description of how the interferometer works, parallel light leaves from the zygo or the interferometer. It passes through my bonded glass, as you can kind of see in the middle on the little fixture. But the ray is then slightly deviated as it goes through. It hits the mirror, it was reflected back, goes through my bonded glass again, deviated once more, and then returns to the zygo. And that overlapping of rays is what causes my fringes. It is an interference patterns of rays passing through one another, and I'll show examples of fringes a little later. But with that, it shows me the peaks and valleys on the surface, trying to see how smooth or how flat my surface is. So when I first started in the lab, I was really just trying to get a feel for how the instrument worked. And here is my very first setup. On the far left, the interferometer gave me data of this big, large blue mirror. And I'm essentially using that as my standard, as my perfect flat, the thing that I want to mold to. And I started off with just using a single sheet of glass attached to this fixture here. And having used the interferometer, Avis gives me this data. So, as you can see here, there is obviously this height difference throughout my glass, but that is just a result of my fixture, seeing as it is not stabilized on all sides. So with how I first had my fixture, it created a bend in my mirror, and so I now knew I had to have a different setup. Which leads me to my fixture setup number 2. So here now, instead of using the large blue mirror, I opted to use a smaller, also still very flat and smooth surface, or flat mirror, because I needed to be able to remove or transport the mirror from the clean room into the materials room, where I would be bonding my glass to that mirror. And here is an example of, is my first run using bonded glass and using that in the interferometer. As you can kind of see in the middle, I have the epoxy and two of my glasses bonded together and using the interferometer. It gave me results I was not expecting. So here, those little lines up top, those are fringes, and I'm supposed to be able to have fringes all throughout that. But for some odd reason, using the interferometer, as it went through the adhesive, I was not able to pick up any sort of data. So it gave me data everywhere but where the adhesive was, which was not very helpful. And so we then were like, okay, what can we do now if that's not going to work? Well, let's try to use one of my coated pieces of glass, and that actually made matters even worse. So here is just what I would first start to see when trying to align my laser with my mirrors. Typically, you'd want to see two red dots, and I would put those dots together, indicating that the incidence ray, the ray that's going out, and the reflected ray, the ray that's coming back in, would be aligned. I don't know about you, but I see no dots. Which made trying to obtain surface data impossible to obtain. And with that, we're not entirely sure why that is, but that is something we'll hopefully figure out in the future. So then just trying to show you a bit of the fringes and how everything went downhill from here. This is what we would want. We'd like to see fringes. With this, we can get surface data and make adjustments from there. This is what we got when we only had bonded glass and not a coated piece of glass. The laser is just very distorted. It wasn't able to go through the epoxy, couldn't pick anything up, so no interference pattern. And then absolutely nothing. Having used my bonded reflected glass, I wasn't able to get any fringes. I could not check any surface smoothness. So no data for surface variations were obtained, unfortunately. However, even though we weren't able to get that, we did succeed on two major issues that honestly was not sure we would be achieving during my time here. Thanks to Joe and his help, we had no air bubbles on my adhesive. We also had no dust particles thanks to the help of Rick and Suzanne. And then unfortunately, we wasn't able to get the surface variations. So then finally, what about plans for the future? So we have our goals. Having learned from our mistakes, we have many ideas kind of in plan, but firstly, we need to find a better spreading method. One of the issues that we believed caused me not to have any data with my bonded glass is that my epoxy did not spread all throughout the glass evenly, and so that probably created an issue. But once you're able to achieve that, we would like to stack more glass, and then also finally use a curved mandrel instead of just a flat surface, which is more realistic for X-ray telescope optics. And so once again, just want to give a thank you to all of these people here, specifically Peter Cheimets and Ed Hertz, my mentors, and everyone that definitely made this project possible. So that is all. Thank you.
Fantastic. Fantastic, Lenice. Thank you very much. So we have time for some questions before we go into our coffee break. So, Jenna.
Really nice talk. Thank you. Fancy. I liked your explanation of interferometry. But I was wondering, so I also suspected, and I had a conversation with Peter about this, that the reason you're not seeing anything is because the glass, it's so distorted that you're just not getting interference.
Yeah.
So if you're, do you have ideas for how you would make the spreading better? So presumably like your epoxy is pulling the glass into a shape that's not allowing you to, that's distorting the wavefront. And how would you change the spreading to potentially, if you were going to continue?
So one of the ideas Peter and I had discussed was instead of simply placing one glass on top of the other and kind of having a force kind of pushing it down, we were thinking maybe having the epoxy or having the glass with the epoxy spin, thus allowing it to kind of like having that sort of pull along the epoxy, allow it to spread more evenly throughout the glass, and hopefully not have that pulling effect that's simply just adding drops created. So hopefully that's the main idea that we're working on.
Callie.
Can you explain how an ultrasonic bath works, like to clean the glass?
Yes, I will try my best. So Oh my goodness. Oh no, it's fine. I should have prepared for that question. So when we used the ultrasonic bath, we had essentially, well, the bath, which had a sort of fluid in it. We had a beaker with also another sort of fluid, we'll say the deionized water, and we had my glass inside that beaker. So when turning on the waves, it just causes a whole lot of, how do I describe it? Oh my gosh. It's just like chaos in a bottle. So basically, every little dust particle, anything that is not glass is essentially being ripped off of my glass, just being pulled by the water off of the surface to where when we take out the glass, it is completely spotless. Hopefully also like very dry. I feel like my mentor could give a better explanation of how that works. If you want to try to help me.
Right, well, you just didn't use the word cavitate.
Cavitate.
So when the ultrasonic waves hit the surface, they cause the water to cavitate, which means the water just immediately goes to gas. And at the instant that it goes to gas, wherever it hits, it explodes whatever is on the surface off. And so hopefully the pressure levels of the cavitation are lower than the destruction pressure of the material you're using, but higher than what it takes to remove the dust.
Did you ever break glass putting it in the bath?
Surprisingly not, no, but I feel bad for all the dust that was in there.
Midge.
Great job. I was curious, in your discussion of future work, you mentioned that you would foresee trying to stack additional layers of glass as well as curving the mandrel. Can you speak a bit as to why that is particularly desirable for X-ray optics?
So as far as stacking the glass, I did a bit of research on glass stacking. So kind of using using NuStar, for example. Their optics is using a shelling method, which is a whole bunch of mirrors that are layered one on top of the other. And that method allows us to have more collecting area or a wider field of view. And then as far as having a curved mandrel, typically for X-ray telescope optics, there is, in order to collect data from these stars, we use a method called grazing incidence optics, where essentially when the light from a star comes in, we have our optic, which is typically a parabola shape and a hyperbola shape, and those are attached together. So kind of imagine one big cylinder, but one is parabola, the other one is hyperbola. And when the light comes in, it would skip or hit the parabola, skip over to the hyperbola, and is then directed into the detector, allowing us to get our data. Now, by me starting off with flat, that's just not realistic, as we would not be able to get that skipping method that is needed. It would most likely just be absorbed, as is typical for normal incidence optics, where light is just simply reflected off, but that is just not how X-ray works for stars. We need that skipping effect. So that's why we want to have curved, but starting off with flat just seemed a bit more possible for these 10 weeks.
Kathy.
This is more of a comment. No, just following up on Midge's question, I'll just put out an advertisement that we actually have the engineering model of the mirror for the X-ray telescope, which is on Hinode and is a grazing incidence telescope. We have that down in Mission Ops, and I showed it to some of the students at some point, but if anybody else wants to take a look, I'm happy to give you a little tour of what a real X-ray mirror looks like.
Time for one quick question. Okay, you don't want to? Okay, you're okay.
Thanks. I wanted to say that's a very nice talk, Lenice, and to make the comment that it's so difficult to give, especially for young people, to give an experimental talk, and especially when you come in to a lab where you know very little, and when your results are more negative than positive. It's extremely difficult to stand there and give a talk. So I think you did a great job. It's a wonderful talk.
That is Suzanne, by the way. She's the best.
Peter has a comment.
Yeah, I wanted to thank Lenice. She came in and I gave her two options. One was hard and the other one was impossible. And she took impossible. And I think for the rest of the summer I realized that there was a failure to communicate. Pretty much we do impossible for lunch here, so we don't use that word much. So when it's impossible, it's sort of like, well, we're going to reverse gravity, we're going to change the orbit of the Earth. So this one was really, really hard. So just to get away from the word impossible, there are 5 goals in order to get to the point that we need to get to. She knocked 2 out and got stuck at the 3rd. But it's a process that all of the other people who are working on this is a very, very hard, long-standing problem in X-ray observation. And everybody else has been working 10 years, and nobody's gotten really close yet. So this was a really good start.
Fantastic. All right, so now is our first coffee break. It'll be 20 minutes. So we will reconvene at 10:45. So get up, stretch your legs, get something to drink, and we'll see you in 20 minutes.
Good talk.
You did a great job.
Yeah.
Is it on? Hello.
It's on now.
All right.
Let's see. Like 45 seconds till you have to start, so whenever you're ready. All right, welcome back, everybody. We're all stretched and limber, so because we've got a few more talks to go through. So first, we got Callie Garcia from Harvard. She's going to talk to us about some prominence eruptions. So whenever you're ready, take it away, Callie.
So hello, my name is Callie Garcia, and today I will be investigating the thermal evolution and helium abundance of a prominence eruption. My project is currently focused on tracking a prominence eruption from August of 2010 at the Sun, collecting information about its ion composition, temperature, and density. This information was collected at different physical points in the prominence and also at different points in time to track the prominences of evolution. And I hope to compare these findings to in situ observations close to Earth. And in situ simply means it's taken at the site. So as opposed to remote observations like imagery, this is stuff like particle detectors. To understand my project, it's important to understand the basis of what a coronal mass ejection is. A CME is an eruption of plasma and magnetic energy that occurs when a sun's magnetic field lines are destabilized at a filament. We have a video here of what a coronal mass ejection can look like. Now, CME has three main structural components: a bright, dense front, a low-density cavity, and a highly dense filament core. And when I say filament, prominence and filament will be used interchangeably for the purposes of this presentation. They mean the same thing, but from different angles of observation. The filament core is what's of interest to me because its composition is actually different from that of the rest of the coronal mass ejection. It's much denser and much cooler than the surrounding material, and therefore has less negatively charged ions, making it one of the few places at the Sun where absorption takes place. But I will get into that later. But this is important because it means that we can distinctly tell when the material we're looking at is prominence material. And it means that we can tell when what we're observing is from a prominence eruption. We can in turn use the absorption features of prominence material to learn about the temperature and density properties of a prominence eruption's evolution. Yet, for reasons currently unknown, prominence material is rarely observed in situ. And we do not know why this is. We don't know if this is because prominence material's different ionization just doesn't make it all the way to particle detectors close to Earth, or if this is because this prominence material is so sparsely spread out by the time it reaches Earth that it's just rarely detected. And we also know that when prominence material does reach particle detectors close to Earth, its ion composition is different from that measured close to the Sun, and we do not know why this is. Therefore, my project seeks to explore this phenomenon by examining one of only 14 prominence eruptions that have been identified to have data both at the Sun and in situ from particle detectors. And I hope to use this exploration to understand the evolution of the prominence both close to the Sun and as it travels outward in space. And having these multiple independent data sources will allow me to more rigorously compare my results and also to serve as constraints to my research methodology as needed. For example, my work with the Solar Dynamic Observatory's AAA instrument required ion abundance constraints that I took from in situ wind mission, wind mission data of the eruption. And you can see that here, where the ion composition, the top three plots, changes suddenly. That's when the prominence material passes through particle detectors at wind close to Earth. So for the past 2 months, I focused on the eruption at the Sun using the AAA instrument on SDO. I constructed small boxes on AAA images that followed out the same patches of prominence material over the course of the eruption, and did this for several different patches of material to create an array of tracks that I could take data from to track the prominence's evolution. The tracks I created for AAA are seen here. For each box and each track, I collected data on the intensity of the material in 4 different wavebands: the 304 angstrom, seen here, and the 211, the 193, and the 171. I was then able to use this data to calculate temperature and density values for the material in each box. But to explain how I did this, you need to understand the general concept of radiative transfer. Radiative transfer is a term used to describe the transfer of energy through electromagnetic radiation through various processes. To describe the two main processes of radiative transfer, let's picture something that gives off electromagnetic radiation, like the sun. Ions in an excited state are flowing out from the sun constantly, and they flow out in all sorts of different wavelengths. And often to get out of that excited state and back to equilibrium, the ion will give off a photon. This process is called emission. But when prominence material comes in front of these outflowing ions, something different happens. Prominence material has all these electrons floating around because it's less highly ionized, and therefore the ions flowing out can collide with these excited state ions, transferring their energy into kinetic energy before it has a chance to be released as a photon. This process is called absorption. And is the reason why prominence material can appear darker than the surrounding plasma. The prominence material is seen here. Because of this whole process, the wavelengths that enter the prominence material have a different observed intensity when they leave it. Using a simplified version of the radiative transfer equation, we are able to neatly relate background intensity and observed intensity to a wavelength-dependent constant, which we could then calculate. This constant is related to a wavelength's waveband region, which groups wavelengths by the main ion they show in absorption. You'll notice that the 304 angstrom waveband belongs to group C, while the 193, the 211, and the 171 all belong to group D. This becomes helpful later. Using the background and observed intensity we took for each box of our AAA tracks for the 4 different wavelengths, and using the wavelength-dependent constant of each wavelength, we could then plug these values into this equation for column density, seen on the left, which produces a line for each wavelength. Plotting all the lines for each wavelength together gives us a plot like this one. You'll notice that the different lines have different behaviors, and these behaviors are determined by the wavelength regions. So you can see that the 304 plots a different shape from the 195 and the 171, and in my case, the 193 as well. And looking at the intersection points of the different waveband regions can tell us about the temperature and density value of the prominence eruption at the box that we're observing. But this just gives us the temperature and density of one box at one point in time, and we're trying to track the evolution. So we need to do this for every box at every point in time on each track. And doing so will give us data on the entire track. So here we can see the temperature and density of the first 2 tracks. I do have data on the other tracks for AAA, but for clarity's sake, I'll keep it to just 2. And you can see that material that is close together, as these first 2 tracks were, has a similar temperature evolution. However, there's an interesting thing going on with the density evolution we don't really see as clear of a trend. And we suspect that this is because from the angle of AAA that these measurements were taken from, the prominence material is actually shooting out in the direction of the observer, causing a pileup of material in the background and skewing our density data. We hope to address this in the future. But for now, our main conclusion is that the prominence material remains cooler for significantly longer than previously observed active region filament eruptions. My methodology relies on the fact that the material that I'm looking at remains in absorption, and I was able to continue the work of my methodology for as long out as the frame of AAA would allow me to, which is several hours, and that's several hours longer than other active region filament eruptions have shown to be cool and in absorption for that to even happen. In the future, I plan to look at the same prominence eruption from the new angles of the stereo A and stereo B missions. This will allow us to have a better side profile angle of the eruptions. As you see here, this is a plot of all of the probe missions that I'm using with their placements at the time of the eruption. And this is the outflow direction of the prominence eruption. So we'll have 2 different side profile angles to compare from. And here we can see the planned tracks for stereo A and also a perspective of what the angle of stereo A will capture for the prominence eruption. We hope that these new angles will provide some insight into the material's density trends, as well as add to the temperature data for a more three-dimensional understanding of the eruption's temperature and density evolution. Additionally, this multi-perspective view will allow us to determine the eruption's outflow velocity. We can then use this, along with our knowledge of the eruption's other properties, to model the eruption's ionization and recombination history as it heads towards Earth. And we can compare the data we gather to the model from the model to recorded carbon, oxygen, and iron ion distributions of the prominence material as measured in situ by ACE-SWICS. Clearly, there's much more left to explore. I would like to thank, with help on my research, my mentors, Yami and Sam, the other mentors and the other interns, my parents for their patience and emotional support, and my dog for his emotional support. Questions?
All right, you're all killing it on time, so we got plenty of questions here. All right, who wants to go first? Sophia.
That was so good. But yeah, I was wondering, how do you know that you're following the same prominence material across all boxes of your track?
That is a great question. Okay, so I use what's called difference images. One of the difference images is seen here. And a difference image simply takes two images. Here it's two images from AIA and the 304 angstrom waveband. And it compares how much material has entered and left each pixel across the 2 points in time. And so stuff that has entered each pixel is shown in a lighter color, and stuff that has left each pixel is shown in a darker color. So by using the lightest patches, we can see where the outflow of the prominence has led to over that time step. So by following the same box of light material, you can tell that you're following that prominence material as it moves out.
Kathy.
Hey, I have a comment and a question. So I'll start with the comment, which is that at the beginning of your talk, you showed the sort of classic three-part structure of the CME light bulb looking thing with the core and then the bright bit, which is usually thought of as the prominence material. I did not know this until 2 days ago, but I ran across a paper a couple of days ago using stereo data where they hypothesized that bright core is not actually the prominence material, but is actually the flux robe that Katie was talking about in her talk. So that's kind of interesting and might be an explanation for why you don't see the prominence material very often in situ. That was something I did not know until I came across that paper.
Interesting.
My question is actually sort of related to Sophia's question, but it has to do with the stereo movie you were showing at the end of your talk. Yeah, let's go there. Yeah. So are these boxes, are they the same at the same locations as your other boxes, or are these new boxes? Are these just positions that you picked that don't necessarily correlate with the boxes from the AIA point of view?
This is new angles. The material from AIA, from the frame of AIA, this material would all be on the right-hand side. Unfortunately, we have a very, our view is kind of 90 degrees to what it is from AIA, right. So it's really hard to see where the material matches up, but we do have plans in the future. You can see in part of the eruption, you can kind of see the backside of that like flux rope looking thing. And so we do have plans in the future to hopefully look at that backside and compare that to what would be the corresponding boxes from stereo B when we have that side profile, and to hopefully do the same from the perspective of stereo B corresponding to these boxes here.
Great, thank you.
Any other questions? Got plenty of time. Someone has to have one. Kathy has another question.
Do you have any plans to, looks like this event has stereo data. Do you have any plans to look for other events where you can maybe use something like Solar Orbiter to do a similar kind of thing?
I have not currently talked to my mentors about exploring other events, but I do think it'd be interesting to explore, of the 14 mentioned prominence eruptions that are detected both at the Sun and in situ, I think it'd be worth exploring the other 13 and seeing, especially just the fact that this prominence material has remained in absorption for so long. I feel like that could be part of the explanation for why that material seems to be preserved in situ only for those 14. So I think it's worth investigating why, if this is a trend, this extended absorption period is a trend with the other 13 prominence eruptions, and maybe that's the characteristic that sets them apart and allows the preservation of their material. Oh.
Midge has a question.
Hi, Callie. Great job. I was wondering if you could speak a little bit more to your process of building the tracks themselves and like what that looked like from your end, what that was like for you.
Well, all of the tracks were built by hand. I picked patches where at the very first time step of the prominence eruption material looked the brightest in the difference images just for simplicity's sake. And I tried to get as spread out a view of the prominence as possible to take as much data from as many different regions as possible. And it was all done by hand, so you go difference image by difference image, trying to follow the material. You pick your coordinates for your first box, and then for every difference image after that, you try and just pick the coordinates by eye that fit that material the best. And it's a big trial and error process because there are some data traces that would suggest to you that you are looking at the same material. And so it was a lot of repositioning my coordinates to make sure that I did have those little signatures that made it clear that I was following the same material. And a lot of mistakes in that process of not having the material and not having my L of T plots show up clearly because of that material and then starting all over. So it's certainly a trial and error process. It's a lot of working by eye, but the difference images are a big help in that you can track and you can have the general area of the material before you go to set your coordinates.
Any other questions? Kathy again.
Do you have any ideas for how you might automate that process? It sounds like it would be a challenge if you wanted to do 10 events. It might take you a while to do it all kind of by hand. Have you given any thought to how you could maybe automate it so that it would be less time consuming?
Because this kind of works on a by-eye system where you have to just pick coordinates, assess how well those coordinates work for the track, and then keep picking them until it works. The only thing I can think of is a machine learning system that could also make those adjustments and recalibrate. I can't imagine just having some sort of program loop that creates that because I wouldn't trust to the effectiveness of something that can't make those adjustments on the fly.
You should talk to the Astro AI people.
Yeah.
We have time for one more question. Going once, going twice. All right, let's give another round of applause for Callie. Disassemble here. There we go. All right. There we go. All right. So our next talk is a bit special because it's not a current RU student. It is a returning RU student who came back to continue her work that she did last year during her RU. So here is the long-awaited sequel to her award-winning talk on CMOS detectors from last year. So let me get this going here. Yeah, let's Oh, yeah, we don't want spoilers. Okay. Yeah, there we go. Yeah. Kathy's got it reversed from what I have. So. All right, let's get rid of this. All right, so here is Juliana Barstow talking about CMOS detectors from New Mexico Tech.
Yeah, Juliana.
Hello. Ah, okay. Cool. So that was a pretty good introduction by Chad, but I work with Christopher Moore and Sophia Sánchez-Maes to characterize the noise of soft X-ray CMOS detectors for the SSAXI-Rocket project. So let's get right into it. For those of you who don't know, SSAXI is a X-ray imager that is set to launch in March 2024 as a ride-along with the High-C rocket you can see here. And it's going to image a high time cadence solar flare. This is where SSAXI is actually on the model. And the main thing I work with is, of course, the CMOS detectors that is right there. Why CMOS? Well, the main thing that we want to use it for is that the typical CCDs we're seeing now have this sort of saturation and blooming effect. And so CMOS can hopefully mitigate that and help us reveal the underlying structures within there. Why can it do that? Well, let's first talk about how these sensors actually work, CCDs. First, we have light coming in. It uses photoelectric effect, and then electrons accumulate, and then they travel from pixel to pixel together, and then they move through one amplifier at the end and go through an output. CMOS starts the exact same way with the photoelectric effect, but it differs in that individual pixels gather charge within there, and then they amplify in parallel before they even exit their pixel to go to a final output. What does this mean? Well, it means that CCD is good at high quality images, but CMOS is great for high speed. It means CCD is good at imaging really dark things, which is what most of space is, but CMOS thrives when we're doing things like the sun because it has a very high saturation capacity. And because of the way they're designed, they're also just more power efficient, they are cheaper to produce, and they are more compact. Why haven't we used CMOS before? Because it has a lot of noise. So that kind of goes back to the core root of why I'm doing what I'm doing, to characterize the noise detector. The sensor that I worked with this summer was a commercial off-the-shelf Teledyne E2V CSM20. This is not the sensor going on SSAXI, but it was what I worked with for my data collection. So here's a basic model of it. This is the sensor itself. This is the mechanical part for additional length. This is the sensor board, and this is the processing board. Early on in the summer, we had problems connecting the sensor board to the sensor itself. And if you look very, very closely, you can see that these pins are actually misaligned. And it's very slight, but it's a very big problem. And so we couldn't actually connect it without putting a bunch of force on our sensor. So we thought, hey, we'll add an extra layer of pins, and that worked great. But that solution created a new problem, as such is life with instrumentation. So that length part was no longer length enough. So I quickly modeled up a new one, and we were able to attach them all together, and we have our working sensor to test with. Why are we using these sensors? Well, first off, why Teledyne exactly if it's not the one going on SSAXI? Why do we care? Well, SSAXI has been delayed with testing. I was originally meant to test with SSAXI, but it's been delayed, so I'm working with Teledyne to kind of get that procedure set up and get the code working so that when we do have SSAXI, we can kind of just plug and chug. It also is just kind of a baseline for comparison, and it further just justifies why are we using a custom sensor for SSAXI. It can kind of give us like what our sensor can do for us in comparison to one that you can just buy off the shelf. Why do we test in general? Well, it's really important to understand how sensors behave in a stable environment. The sun is very unpredictable, and we cannot control it, but we can control our experimental setup, so we have very few variables that allow us to solely focus on characterizing the noise of our detector. And the better we understand our sensor at this small level, the better we can work to actually mitigate this noise in the future. So this is our setup. As I said, very basic. We utilize an integrating sphere and a black box. So the QTH is a quartz halogen lamp, so light comes through there, it bounces around the integrating sphere, and it moves in all directions until it finally gives us kind of a uniform light production to our lens, goes through baffles, and ultimately goes to our sensor. And this is what it looks like in real life. So again, our quartz halogen lamp is it's kind of hidden, but it's back there next to the sphere. We have our lens, our baffles, our sensor, and then this thing in the middle is not always here for testing, but we have it in the beginning. It's what we call an eye test, and it kind of just makes us see that we can properly align our focus and see what's going on. So you can actually see numbers there, which means that, yay, it is working. It is getting what we want it to. what is the data going to get us ultimately? Well, the main goal is to create what's known as a photon transfer curve, and it is just a really good way to characterize the noise in one nice graph. So as I said, we can vary the illumination with the quartilligent lamp, and so each illumination level is going to give us 1 point on the graph. So we will change illumination over time and ultimately get many points. And in an ideal world, we get a very nice curve that looks perfect and beautiful like this. And you can see that there's kind of these distinct regions happening already. So we have this first area, which is called read noise. It has a slope of 0. We go into shot noise, it has a slope of 0.5, and we go into fixed pattern noise with a slope of 1, and then finally we hit saturation. And so we have our very distinct, beautiful regions. These slopes are very important. If the fit is not precisely or very close to these values, we can't characterize these other parameters well. So if you trace the line from the fixed pattern, you get what's known as the quality factor for fixed pattern noise. If you trace it for shot noise, you get what's known as the gain. And if those slopes aren't accurate, then those aren't accurate either. So it's really important to fit to that. And we can also get our saturation limit. So before I actually show me my data, let's break into what these noises are actually telling us. So first up, read noise. As I said, it has a slope of 0. That's because it's kind of independent of signal magnitude. And it's kind of what you get from the inherent process of how detectors read out when the electrons are converted from charge to voltage and then amplified. It's that process that causes this. And CCD, bringing this graph back, you can see that there's little variation between read noise in pixels because of the way they're grouped together, whereas CMOS, we have a lot more variation because of that individual change in the pixels. Next up is shot noise. It varies with the root of signal. And shot noise is essentially how photons vary when they spatially arrive at the detector. So here we have a simple 4x4 simulation where we'll simulate 20 photons hitting a detector. What happens is at the end, you have some that have been hit by like 5 photons, and you have some that have no photons. And that's exactly what shot noise is. It's how that varies. Of course, this is just a simple simulation. The actual images are going to be much, much larger. But in general, the more photons you have coming in, the less of that fuzziness you can see. So here we have the 2 photons versus the 512 photons, where it's a lot smoother. Next up is fixed pattern noise, which varies linearly with signal. And basically, it's exactly what it sounds like. It's a consistent pattern that arises over your frames that basically hides the true image you want to see. So again, basic example, we have that stripiness covering an image that we want to see. Thankfully, it's actually quite predictable by sensors, and we can remove it by frame differencing. So here's a lovely photo of a cat I found in a paper. There's a stripiness here, but after the frame difference, you can see the cat more clearly in all its glory. Also important to know that for CMOS, we expect the region to be larger because of the different DC offset pixels in each of that, the way it works. So this region should be larger than what we see in the CCD one. Finally, we hit the full well. And now you can think about this as an actual well. It's where it gets its name. In the same way that a well will fill up with water, our pixel will fill up with photoelectrons over time. And so full well is the amount of charge that a pixel can take before it saturates. And so if you look here, we have 4 very divine pixels when the well is pretty much empty. But as the well fills up, they start blurring together, and you can no longer distinctly tell where the original circles were as much. And again, simple example, it gets much worse for actual sensors. Now, at this point, the pixel can't really accept any more electrons. So in CCD, that's when blooming comes into effect. It spreads into other pixels, and you get this kind of stripiness that's known as blooming. And CMOS, one of the reasons we would like to use it is because it theoretically should not do this, because it has other transistors as like a backup to prevent this. Cool. So what does our data actually look like? So like I said, we take images at different illumination frames. So as that light is going to get brighter, we're going to have images at each different frame. And we can actually, we can actually see some of the noise I just talked about in these images. So first up is this dark frame. That is when there was no light on. And this one's pretty hard to see. But if you look very closely, there are some difference in pixels there. So even though you have no signal coming in, there's still some noise happening. Then we have the shot noise. As we're getting brighter, again, we're seeing less of that fuzziness over time. Fixed pattern noise, that one's pretty clear. You see that stripiness again. And then we have saturation. We have these weird spots in our sensor. We don't want them anyway, but saturation, you can tell they're becoming less prominent because the pixel is saturating, so you can no longer see it as distinctly. And now, the actual data that we got from this. This is the initial plot, and hey, it kind of looks like what we want it to. Not exactly, but we can characterize it a bit more. So just as before, we have first, if we isolate our dark frames, we have the read noise region. Then we have the shot noise region, and you may be thinking, hey, that's not a very good fit. And you'd be right. It is not a good fit. But that comes back to the point of you want to have a fit to where it's at 0.5. That is the very crucial in order to get the gain. And so this is actually, my code basically finds the optimal positions on this graph that create that 0.5. So this is actually a better fit for the ones up top and not necessarily all of it. In an ideal world, it would fit more beautifully. In this one, it did not. Same with the fixed pattern noise. not the best fit, but it is a slope of 1. And then we have the saturation noise. And yay, here is our regions. Not as ideal as we'd like it to be, but it is kind of distinctly giving us those positions. One thing to note is that I mentioned that we'd expect FPN to be larger. It's not. I took a lot of different curves of this. You can do it with different subarrays of the frames. This is just one example. In some of them, the fixed pattern noise is much larger, sometimes so much so that it entirely covers the shot noise. I don't exactly know why that's happening. The main theory going right now is that these parameters, the 0.5 and 1, were developed for CMOS or for CCDs. It could very well be different for the CMOS. But just as before, we can trace back our slopes and we can get values for gain and the fixed pattern quality factor using these equations over here, and we can also see our saturation point. And the good thing is that because this is a commercial off-the-shelf product, we can actually compare our values to what Teledyne is telling us they are. Sigma read is actually really good, about 0.2 electrons off. Unfortunately, the goodness ends there, as our gain is about 1/4 of what we'd expect it to be. Our fixed pattern quality factor is about double, so we're getting a lot more fixed pattern noise than we'd expect to, and we're saturating substantially sooner. Now, why is this happening? It could just be a bad sensor, but there's also a lot of other reasons we could do this. Number one is we tested in different conditions they did. So they cooled their sensor. We did not. They used a gigantic processing board. As you saw, ours was very tiny. They used an LED, we used a core halogen lamp, and all those things could definitely factor in at these differences. We also have imperfect dark. So our lab setup is right next to a very beautiful window, which is lovely when you're in the lab all day, but it's not ideal for taking images. So we closed the window, turned the lights off, but there's still going to be some issues there. Our software is very limited, and by limited I mean that you really can't do much other than take a picture. And so we can't even quantify the integration time. The way we quantified it was just physically timing it myself, and so I am not a computer who can do that perfectly, so there's going to be some issues there. And like I said before, our sensor is under mechanical stress, and so even with that extra layer of pins, there's still some stress happening, and that could still cause a lot of problems. And so that's kind of the main results of the photon transfer curves. Like I said, I took many different versions of this. This is just one example. You can get a curve for any part of the CMOS array, and you can see some variation. The next thing we were trying to do was linearity testing. So at the same time we were taking data with our CIS-120, we had a photodiode inside of an integrating sphere. Now this is what it came out to be for the sensor, and you can say, hey, that's not linear. So what's the problem there? Well, we can't actually quantify our light source, which I'll get more into a second, but we can look at our photodiode. We purchased a NIST-calibrated photodiode for reference. So here's before it came in, and then I assembled it, and we were able to put it into our integrating sphere, and it gave us a way to actually quantify our light source because it had an actual current attached to it. So we get a value rather than just a relative. And so this one, also not linear. But it matches the other one, which means the problem kind of lies in the way we're taking data. And by that I mean the way that we change illumination level is not by physically increasing intensity. It's we have a shutter that opens and closes. And when I'm opening that shutter, I have no reference for how much it's open or closed when I'm taking data. And so that is not a perfect system. It shows you how linear I am at taking data. It's kind of good, for doing it by hand. But in an ideal world, you want a slope of 1. That is not a slope of 1. So in the future, and by future I mean tomorrow, we're taking better data. Our plan is to change methods. We're going to use an LED instead of a core halogen lamp because it's more precise, and we are going to change illumination by using a power supply. We can actually see a physical value changing rather than just me instinctively turning a little knob. So what's next? Well, we're actually going to test SSAXI after I'm gone, unfortunately. But another part of the summer was dedicated to changing out our other lab system with a vacuum chamber. So before we had this smaller chamber, we wanted to put this bigger one so SSAXI could actually fit in there and be tested. There's us changing it out, and there it is currently. And so now SSAXI can actually fit in here. And so the next steps are to test SSAXI in here, as well as in my setup with the black box, and hopefully get some good data before we send it off to go to space. And yeah, I want to thank, of course, my mentors, Chris for allowing me to come back this summer, Sophia Sánchez-Maes for really helping me out with the setup and everything, everyone in my lab group, you've all been very, very helpful, everyone at CDP for helping me along the way. Yeah, it's been a very good time. Any questions?
Excellent, Juliana. Thank you. All right. Questions? Nick.
I had a question. You had mentioned with that the slopes for some of these noise types were based upon the CCD values. And I was wondering, are those values, were they found empirically, or is that something from theory?
They found those empirically through testing. So I guess it might have been theoretical first. I'm actually not sure. But through many testing of CCDs, those were like the parameters that they found.
Okay, and so they might be different.
They might be different for CMOS, yes.
Thank you.
All right, got a question over here.
So in the shot noise region of your noise versus signal graph, you have like the linear slope of 0.5.
Yeah.
But then you also mentioned a quantity related to the shot noise where that line intersects the x-axis.
Yes.
That goes as the root of the signal. And like, what is the relationship between those two different like relations? If that makes sense.
Do you mean this equation kind of?
Yes, that's what I
Yeah,
mean.
so this is the gain. The way we get the line before, we actually isolate it from the original just deviation. And then this gain factor is kind of telling us how much our signal is being amplified in a sense. And so at this 0.5 slope, when you trace it perfectly, you get that gain factor and you can quantify it from this square roots relationship.
Charles?
Thank you, this is great. So when you saturate a pixel on a CCD, generally speaking, the photoelectrons are conserved. They just pour over into neighboring pixels.
Mm-hmm.
Is that what happens in the CMOS detectors? Because I don't think that...
No, CMOS has backup transistors. And so that's what I was kind of speaking about in this one. CCDs, they will go over to the next pixel. CMOS has what's called a 5T transistor system. So rather than going into the next pixel, it will go into those transistors before that happens.
So that's built in. You don't have to twiddle a switch or recognize that's going on.
Yeah, it's built into them.
And you record those saturation quantities?
What do you mean? Sorry. Like.
Well, do you know how many photoelectrons have gone through that process? You know, once you saturate it, your backup system comes in.
I'm not sure that I have a way to quantify that with the way I've been taking data.
Okay, right.
We can.
Okay.
We have to do some extra electronics, but we can.
Okay, thanks.
Any other questions?
Great question, Charles.
Yes.
So about the photon transfer curve, is that from the full detector, or you're choosing some?
This one is a subarray. For the photodetector, I also have data for that one. The main differences you'll see different, like, it's the same shape regardless, but it's going to just be different variations of like where it actually saturates, the shape of some of the fits. But this one in particular, I think it says about 100 by 100 pixel region.
So in that case, the fact the saturation section is much larger than other devices, maybe due to that the full well depth has some variation relative to signal baseline. Maybe that's causing the apparent enlargement of that section, maybe.
Yeah, that's an interesting point. I'd have to look into it, but yeah, that is a great point.
Any other questions? Kathy.
So do you know when the SSAXI sensor will be here and when you can do that?
That is not up to me.
And of course not, but
yeah.
Just wondering if you had that information.
I know that last I heard it was looking promising, and so in the next few weeks, ideally, right after I leave. So.
So hopefully in a couple of weeks, someone will be able to take the sensor and run your processes on it, and it'll be all plug and play and be able to characterize it.
I'll be handing my code over to Sophia, who I believe will be doing that.
Kathy, any day now. That's what the engineers are working on the camera system right now. Any day.
I have time for one more question. If not, I have one. So you mentioned that compared to a CCD, a CMOS detector can have more spatial variability in read noise, and that struck a lot of dread inside of me. So how do you anticipate in a calibration sense to account for that?
That's a great question. I will say that even though it varies more, it still kind of trends to a general area. Yeah. So it's just something more to be aware of that can happen. You can take more samples perhaps, and try different regions to try and mitigate that or get like a better idea of what your mean is. So it's a little bit more difficult, but I think you can still account for it quite easily.
Okay.
I would hope.
Yeah, one would hope. All right, maybe one quick question. Yes.
Okay, so unfortunately, I didn't get to hear last summer's talk, but I was just a little bit curious in like a couple sentences if you could summarize the work you did last summer so that we could kind of see how the 2 summers have related.
So last summer, sad to say, a lot of our instrumentation was just not functioning last summer. So I would say the most valuable thing I got out of it was actually getting a lot of the background information and understanding our system a lot. But because it was not functioning for about 8 weeks of the summer, we did not get as much data. I did not do anything with PTCs last summer. This is an entirely new thing for here. But I did look at the characterization of noise and took some, even with our not very good data, I took some of the processes and tried to characterize noise from there. And I used some of that code this summer to help me make a more defined graph. Yes.
Excellent. Let's give a round of applause for Juliana again. Not on the red screen. You are downloading. All right. Up next from Bowdoin College up in Maine, we have Anna Chen, who will be talking to us about X-ray observations of flares.
Not yet? Okay. Okay, perfect. Okay, hello everybody. My name is Anna Chen. For the past 10 weeks, I have been working with Dr. Katherine Reeves and Dr. Xiaoyan Xie to work on my project, spatially resolved thermal diagnostics of a M1.0 flare observed by X-ray telescope aboard Hinode. So I just wanted to go over a quick overview of my project. I'll be talking about the big picture and why I cannot, for the life of me, escape Python. Then I'll move on to some of my processes that I've been using for the past 10 weeks, especially on the flare observed on July 21st, 2016. Then I will end on some results, conclusions, and what I will be doing moving forward. All right. Essentially, my big picture is that I am doing spatially resolved thermal analysis of flares observed at X-ray wavelengths. Thermal analysis meaning I will be analyzing and creating temperature and volume emission measure maps, where a volume emission measure means the density of electrons and a volume integrated over along the line of sight, or the amount of plasma along the line of sight. Creating these maps will help us creating these maps based on different abundance assumptions can help us evaluate models of how flares form and evolve. So let's get the big question out of the way. What actually are solar flares? These are some of the coolest phenomenon on the sun, of course, figuratively coolest. They occur when forces of magnetic tension on the corona exceeds the forces of gravity and thermal pressure, and the magnetic field of the sun breaks and erupts. The released magnetic energy converts into thermal and kinetic energy, which heats up plasma and creates coronal mass ejections, otherwise known as CMEs. And this is just an example of a composite flare image that I created in Python, which I'll explain later. So that being said, how am I getting my data? Drum roll. XRT. So I am using data collected by the X-ray telescope of XRT aboard Hinode. This satellite mission was a collaboration mission between NASA, the Japanese Aerospace Exploration Agency, and the European Space Agency. And it was launched in 2006 from Japan. Fun fact, CFA researchers actually collaborated with JAXA engineers to develop XRT, as Kathy mentioned earlier. XRT utilizes 9 different filters that can be used in combinations of 2 in the filter ratio method to produce temperature and volume emission maps. And the 2 filters that I will be using in my project are BE thin and beryllium mid. This is just an example of how you can determine temperature by hand using the ratio of temperature responses. I will explain this all later. But yeah. So I've been talking about abundance assumptions a lot, so obviously it's very important, but what actually are abundance assumptions and why do we care at all? There are three main abundance models used by the solar community. They are chronal, hybrid, and photospheric abundances taken from the Chianti 10.0 database. These values change as new data from different phenomena, solar energetic particles, solar wind, and the continuum spectroscopy of hydrogen comes in and disproves previous data. There's one crucial term to understanding the differences between them, and that is FIP, the first ionization potential of the element, meaning the energy to remove the first electron from a neutral atom. More specifically, chrono-photospheric elemental abundance ratios is higher for low FIP elements than for high FIP elements. These elemental abundances can reveal mechanisms of how flares form and develop. For example, a photospheric abundance during a flare could support the process of chromospheric evaporation, where photospheric material is pulled up through entangling magnetic fields, and you can see photospheric abundances during the flare. So I created some movies to visually illustrate how the same series of images can look quite different under different abundance assumptions. So on the left, we can see a series of temperature maps created under the chrono abundance assumption, the middle of the hybrid abundance assumption, and the right, the photospheric abundance assumption. The chrono and the hybrid looks very similar visually, but you can see that in the photospheric abundance assumption, there are much greener and much bluer pixels, indicative of a lower temperature. So at this point, I want to talk about how XRT actually calculates temperature, and this is through the filter ratio method. This is one of the primary ways of analyzing XRT data, and it assumes that the corona is isothermal. This has some implications, which I will also get into in a little bit. Basically, using the filter ratio method, XRT turns pixel intensity into temperature responses and then into temperature. This varies with abundance assumptions, as I mentioned earlier, and slightly with time. These are some of the math that goes behind the filter ratio method, which I would be happy to talk about after my presentation. So abundance assumptions are very important to me for creating my temperature maps, but how am I actually getting my abundance assumptions? And this is where the paper by Suarez and Moore comes in. Suarez and Moore takes the time evolution of 21 flares taken between May 2016 and May 2017 using the MINX CubeSat mission. They fit temperature, volume emission measure, and elemental abundances to variothermal fit, meaning that they assume there are two significant plasma components with two different temperatures. And these are two graphs taken from their paper that illustrate these two thermal fits. You can see that there is a higher emission measure component and a lower emission measure component, and the same with the temperature. I highly recommend reading their paper if you want to learn more about this. It's very interesting. By basing our abundance assumptions on their elemental abundances, we can create temperature and volume emission maps that basically show, or best show, what is actually happening on the sun during the flare. And I want to also point out that XRT is spatially resolved, meaning that it can actually pick out specific temperatures of specific pixels, while MINX is spatially integrated, meaning that it takes the average temperature over the whole sun, which is why we are doing a comparison of the two. And by using XRT, then we can make temperature maps that tell us the spatial distribution of the flare. More specifically, I will be using the silicon abundance fitted by Suarez and Moore. You can see from this graph that the purple line is indicative of the photospheric abundance, the navy is similar to the chrono abundance, and the green is similar to the hybrid abundance. I will be picking, I picked 3 points from this flare to basically make temperature maps and do thermal analysis on. One from the beginning of the flare with the photospheric abundance, one at the peak of the flare with the chrono abundance, and one at the end of the flare using the hybrid abundance. Spoiler, we actually do indeed see a two-temperature distribution from XRT data, very similar to those seen from Suarez and Moore's paper. So getting into how I'm actually creating my temperature and volume emission measure maps. The program that I am using is XRTPy, which is a newly developed Python package.
And as part of my project and as a wider effort to make XRT science more accessible to the public, I've been troubleshooting and providing feedback for its developers. And ironically, I decided at the beginning of my college career that I didn't want to take any comp sci classes in an effort to take more cooler physics classes, and it's coming back to haunt me this summer. So yeah, more specifically, I am using a function called XRT team, which produces temperature and volume emission maps using the filter ratio technique. The graph that I showed from the beginning of the presentation, this one is how you would do it by hand. An XRT team basically does that and a lot more using one line of code, basically. So quite tragic if you think about it. This is a temperature map created by XRT team. As you can see, this is a moment in time for the flare that I am analyzing under the hybrid abundance. And just to show you, this is the same point in time using the photospheric abundance. So we can see how they do vary quite drastically. So it was at this point where we ran into a problem of oversaturation. XRT team kept returning holes in its temperature and volume emission maps, as you can see in the lower right-hand corner. The core of the flares kept returning values of 0 temperature, or 0 Kelvin. After some testing, we tested the temperature response ratios, and we found that at the exact locations where XRT team was returning no value, it had temperature response ratio values of 0.5 or higher. And if we look back at the graph I included at the beginning, there is no temperature associated with ratio values higher than, say, 0.45. So this didn't make sense. We found out that this was because the images that we were using for XRT team was oversaturated, which meant that XRT team was disregarding pixels that have ratio values of higher than the threshold. So before we moved on, we had to come up with a solution to solve these saturated images. And the solution we came up with was to make composite images. Composite images are made from one short and one long exposure XRT images. And they basically take the saturated pixels of the long exposure and replaces it with the short exposure of the unsaturated pixels of the short exposure images. Thankfully, this program exists in IDL. But I was tasked to create a simple program in Python to create these composite images for similar reasons as why XRT-Pi was created. So again, I cannot escape Python for some reason. So I was able to create a simple program in Python to create these composite images by using grade maps, which are accompanying arrays to individual XRT images that told us which pixels were saturated, contaminated, affected by dust, etc. And these composite images, or composite temperature and VEM maps, solved the whole problem and made very beautiful XPALs, which stand for XRT Picture of the Week, which everybody should go check out later. So for example, this is an XPAL that I created using a short exposure and a long exposure BE thin map or image. And as you can see, the composite image that I created in Python showed a lot more detail in the flare and around the active region. So I just want to share some of my results. These are the temperature maps that I created. These are the VEM maps that I created for the 3 points in time. As you can see, they are under different abundance assumptions. So what do these maps actually mean, and how do we actually get data and result from them? After creating these maps, I also created histograms of the number of pixels against their individual temperatures. We can see that there is a bimodal temperature distribution very, very similar to the two variable thermal fit taken by Suarez and Moore. And by using these histograms, I was able to create temperature maps that illustrated these separation of temperature ranges. As you can see, the bluer pixels on the right signifies the lower temperatures, and the redder pixels signify the hotter temperatures. I did the same with the VEM distribution. I took the VEM of the lower temperature ranges and mapped it on the left, and the higher temperatures on the right. And you can see that there is a higher density of
higher temperatures near the core of the flare, while the lower temperatures are mostly around the edges. And you can see that a little bit in this map as well. So then I wanted to compare my results with Suarez and Moore. My high and low temperatures calculated from the filter ratio method lie within error of the temperatures fitted by Suarez and Moore. Yay! However, there is a little bit more nuance with my VEM results. So the original plan was to create VEM maps using the photospheric abundance for the first point. However, I realized that this did not fit very well with what was seen from Suarez and Moore, and so I tested it out a little bit, and I ended up with using the corona abundance, which fitted a lot better. So I just want to highlight some conclusions that we were able to make. XRT was able to show a bimodal distribution of the temperature. More importantly, we were able to see the spatial distribution of the high and low temperatures. The higher temperatures are observed in the center of the flare, while the lower temperatures are around the edges of the active region, which is a big point of XRT's spatial capabilities. My high and low temperatures match with the results taken by Suarez and Moore. However, our VEM was higher than Suarez and Moore for the earliest time. Moving forward, I want to look at differential emission measures. So instead of volume emission measure, so instead of thermal measurements across the surfaces of the sun, which is what volume emission measure does, we take the thermal measure along the line of sight. Which is one of the biggest assumptions of the filter ratio method, was that we are assuming the corona is isothermal, which means there is one temperature along the line of sight. So that would be very exciting. And I just want to give some acknowledgements, especially to my mentors, Kathy and Xiaoyan, Chriselle Suarez and Dr. Christopher Moore for asking me, for letting me ask way too many questions, and Joy and Jonathan for helping me defeat Python. And also the box fan in my dorm room. It's been a hot summer. And questions?
Fantastic. All right. So we'll go right into questions.
Hi, Anna. This is John Sullivan, just in case, since we haven't actually seen each other in person.
Yeah.
So I was curious about the abundances is in the Suarez and Moore model. Do they align with either the Chianti photospheric, or do they align with those abundances? Or are they different from both of those?
So they are actually different from the Chianti 10.0 database. Because they were fitted individually to their data, but they are similar to, as far as I can tell, they are similar to the coronal and the photospheric and the hybrid. If I were to use like individualized abundances, I would have to go through spectroscopy, which was something that I wasn't using this summer. Right. But it is something we could work on in the future.
Okay, thanks.
Yeah.
Any more questions? Charles.
Thank you. This is very interesting. So the source material for the corona is the photosphere, right? So I'd expect all the abundances to start out pretty much with photospheric abundances, which I've lived with for decades and love. So what causes the separation? What causes the silicon abundance to change?
So you mean like throughout the flare, or since the silicon abundance started with the photospheric abundance? Yes, yes.
What causes the change when it goes into the corona?
So there are a lot of processes, and this is one of the reasons that we're studying abundance assumptions. Processes such as chromospheric evaporation reconnection, where like plasma is pulled up from different layers of the sun into the corona during the flare. Does that answer the question?
Not completely, but something to think about.
I'll throw in an answer for you, which is the ponderomotive force, is what causes the ponderomotive force is possibly what causes the stratification in the corona versus the photosphere. So the coronal abundances in the actual corona or what you normally see in like an active region or something, you would probably see the coronal abundances. Sometimes during flares, you see these photospheric abundances because of the chromospheric evaporation, and you're scooping up the lower levels of the atmosphere and pumping them into the corona before they've had this chance to separate out.
Time for another question? Oh, we got one in the chat. So, ooh, Helen Mason.
No, you don't have to. Every time you start, ask.
Do we actually have a question?
No, there's one question from Helen Mason.
All right, let me take.
I think you can unmute yourself and ask the question.
Yeah, could you put it in chat, actually, Helen? Mm-hmm.
Nope. You lost her.
Oh, did we lose Helen? I mean, she is typing from the UK, so.
Maybe take another question while you're waiting for Helen.
Yeah. Any other question while we wait for Helen?
So you mentioned that you were using 2 filters, I think the beryllium thin and med. Why did you choose those 2?
So it was kind of out of necessity because for this specific flare, there were only 2 filters that was taking photos of the flare. So, yeah.
I'll add to that. Anna's totally right that those were pretty much the only 2 choices. But with Helen Mason and Julia Delzano, we've actually done some previous work where we've looked at both AL poly BE thin combination and the BE thin BE medium combination, and the combination that Anna is using turns out to match better with other X-ray measurements like those from Minx, like she showed here, and also from XSM, which is another similar instrument on an Indian satellite.
So, and we have the long-awaited question from Helen Mason, who's joining us from Cambridge University. She says, nice talk, Anna. The photospheric abundances during the impulsive phase are indeed probably caused by chromospheric abundances, so we're not sure about why the abundances return to coronal from work with XSM. So more of a comment. Thank you, Helen. All right, and with that, we are going to break for lunch. It will be 1 hour and 15 minutes, so we will reconvene at 1 p.m. And we will start gathering all the foodstuffs in the back here in just a few minutes. So, all right.
Thank all the speakers again.
Yes, so let's thank all the speakers again.